Hello and welcome. Tonight, we'll be exploring one of the greatest transformations in the history of our universe. If you could somehow travel back more than 4.5 billion years, you would arrive at a place that would hardly resemble the world you know today. There would be no blue oceans stretching toward the horizon, no forests whispering in the wind, no birds greeting the morning, no mountains capped with snow, and certainly no human footprints waiting to be discovered. Instead, you would find yourself standing before a planet that looked more like an enormous furnace than a future home for life. It may seem difficult to believe that every tree, every whale, every flower, and every person who has ever lived ultimately traces their story back to this fiery beginning. Yet that is exactly what makes Earth's history so remarkable. The peaceful world we know today was not created all at once. It emerged slowly, patiently, over unimaginable stretches of time, shaped by countless events that at first appeared to make life impossible. So, find a comfortable place to rest. Allow your thoughts to drift as gently as clouds across a quiet evening sky, and let's begin our journey into one of the most extraordinary stories science has ever uncovered. Long before Earth existed, our solar system was little more than an immense cloud of gas and tiny grains of dust drifting silently through space. There were no planets yet, only scattered particles moving through darkness under the quiet pull of gravity. Over millions of years, those tiny grains slowly gathered together. It was a surprisingly gentle beginning. Imagine watching snowflakes fall onto an open field. One by one, they seem insignificant, but given enough time, they form a blanket that transforms the landscape. In much the same way, countless particles gradually collided, clung together, and grew into larger and larger bodies. At the center of this growing family, the young sun ignited, filling the surrounding space with warmth and light. Around it, countless fragments of rock continued their endless dance. Some shattered apart, others merged into larger worlds. Every collision was another small step toward the formation of the planets we know today. Among those growing worlds was the young Earth. But this newborn planet was anything but peaceful. Each incoming rock struck with astonishing force, releasing tremendous amounts of energy. The larger Earth became, the stronger its gravity grew, attracting even more material. Every collision generated heat, and with millions upon millions of impacts occurring over vast stretches of time, that heat had nowhere to escape. Eventually, nearly the entire surface melted. Instead of solid ground, Earth became an immense ocean of glowing molten rock. Rivers of liquid stone flowed where oceans would someday exist. Mountains could not survive because they simply melted back into the fiery landscape. Even the rocks themselves were soft enough to move like thick, glowing syrup beneath an orange-red sky. If you had looked upward, you would not have seen blue skies or white clouds. The atmosphere was dense, heavy, and completely unlike the air we breathe today. Thick volcanic gases filled the sky, including enormous amounts of carbon dioxide, methane, steam, and other gases released from Earth's restless interior. Sunlight struggled to pass through this heavy blanket, painting the heavens in deep shades of crimson, orange, and smoky grey. The young planet seemed alive, constantly breathing through countless volcanoes scattered across its surface. And yet, astonishingly, Earth was still not experiencing the most violent chapter of its early life. Far beyond its glowing horizon, countless rocky bodies continued racing through space. For hundreds of millions of years, Earth endured an almost unimaginable storm of impacts. Asteroids and smaller rocky fragments struck the planet again and again. Some were no larger than hills, others rivaled entire mountains. Each collision carved enormous scars into the molten surface, throwing glowing debris high above the atmosphere before it slowly rained back down again. At first glance, this endless bombardment seems like nothing more than destruction. But nature often hides remarkable surprises inside apparent chaos. Many of those ancient visitors carried something precious. Some brought water locked inside minerals or ancient ice. Others carried carbon-rich compounds and simple chemical ingredients that would eventually participate in Earth's long journey toward life. The same impacts that repeatedly devastated the planet also delivered some of the building blocks needed for its future. It is one of the beautiful paradoxes woven throughout Earth's history. The forces that seemed determined to prevent life were quietly helping prepare the stage upon which life would eventually appear. Among all of these colossal collisions, one event may have shaped Earth's future more than any other. Scientists believe that a young planetary body, roughly the size of Mars, collided with the early Earth. The impact was so unimaginably powerful that enormous amounts of molten rock were blasted into space. Today, the Moon often appears calm and familiar, quietly illuminating peaceful nights. But its birth was anything but peaceful. Its presence would eventually help stabilize Earth's gentle wobble as it rotated through space. Much later, it would also guide the rise and fall of ocean tides, creating rhythmic movements that may have influenced some of the earliest environments where life's chemistry unfolded. It is remarkable to think that one violent collision could later contribute to so much stability. As millions of years became hundreds of millions of years, the young Earth continued radiating its tremendous heat into space. Ever so slowly, almost imperceptibly, the surface began its long journey toward cooling. Nothing changed overnight. The glowing oceans of molten rock remained. Volcanoes still erupted almost constantly. The atmosphere remained thick and hostile. Asteroids still visited from time to time. Yet beneath all of that apparent violence, change had already begun. Like a pot of soup slowly cooling after being removed from the fire, the planet was quietly moving toward a completely different future. No living creature could have noticed it. No observer could have measured the transformation over the course of a single day. But over millions of years, tiny differences accumulated. Heat escaped. The surface became just a little less hostile. The atmosphere continued to grow. And somewhere within this restless young world, the conditions that once seemed utterly impossible were slowly becoming merely improbable. Before long, the sky would begin holding something it had never truly possessed before, in lasting abundance. Not fire, not stone, but water. Its arrival would soften the face of this volcanic world in ways no one could have imagined, quietly preparing the stage for the next remarkable transformation in Earth's long and patient story. For a very long time, Earth still looked like a world that had no future beyond fire. Its surface glowed beneath countless volcanoes. Rivers of molten rock continued flowing across vast plains, while thick clouds of volcanic gases wrapped the planet like an enormous blanket. The young moon, born from an ancient collision, circled overhead, much closer than it does today. Every day, every year, every century, the planet remained restless. Yet even in a place that seemed trapped in endless chaos, change was quietly unfolding. Heat was slowly escaping into space. Not quickly enough for anyone to notice over a single lifetime, of course. But over millions of years, the difference became impossible to ignore. Like a loaf of bread cooling after leaving the oven, the outside began to cool before the inside. A thin, rocky skin slowly formed across parts of Earth's molten surface. It was fragile. It cracked. It broke apart again and again as fresh magma rose from below. The planet was trying to build its first crust, while its fiery interior kept reminding everyone that the story was far from over. Every volcanic eruption added another chapter to this slow transformation. Along with molten rock came enormous quantities of gas escaping from deep inside the planet. It was almost as though Earth itself was breathing for the first time. With each eruption, more steam entered the atmosphere. Carbon dioxide accumulated alongside methane, nitrogen, and sulfur-rich volcanic gases. The sky became even thicker, warmer, and heavier. If you could somehow stand above this ancient landscape, you might have the strange impression that an invisible ocean was hanging overhead. That impression would not have been entirely wrong. Much of Earth's future water was no longer trapped inside hot rocks. It now floated through the atmosphere as enormous quantities of steam, waiting patiently for the planet to cool just a little more. Where all of Earth's water originally came from remains one of the most fascinating questions in planetary science. The answer appears to be a combination rather than a single source. Some of it rose from deep within the planet itself. As volcanoes erupted, they released vast amounts of steam that had been locked inside Earth's interior since its formation. Some may also have arrived from space. Ancient asteroids, especially those rich in water-bearing minerals, likely delivered additional water during the heavy bombardment that shaped the young solar system. Comets may have contributed as well, although scientists continue to debate exactly how large that contribution was. Rather than choosing one explanation over another, the evidence suggests that Earth gradually gathered water from several different pathways, each adding another small piece to an extraordinary puzzle. Eventually, the temperature crossed a threshold. Steam no longer remained steam forever. Clouds began to form. Then, for the first time in Earth's history, rain began to fall. Not the kind of gentle rain that taps softly against a window on a quiet afternoon. This rain met ground so hot that much of it instantly flashed back into steam. Water fell. It boiled. It rose again. Then it condensed once more. The cycle repeated endlessly. It is difficult to imagine such persistence. Not days, not years, perhaps millions of years of rainfall, evaporation, and rainfall again, as the young planet slowly negotiated a peaceful agreement between fire and water. Little by little, water finally began to remain on the surface, instead of disappearing back into the sky. The first long-lasting pools appeared. Those pools slowly joined together. Eventually, the earliest oceans spread across much of the planet. They looked nothing like today's oceans. Their waters were warmer, more acidic, and rich in dissolved minerals carried from freshly formed rocks and active volcanoes. The seas may have shimmered beneath a hazy orange sky, rather than the bright blue horizon we know today. Even so, something profoundly important had changed. For the first time, Earth possessed stable liquid water. It is easy to think of oceans simply as places where life eventually appeared. In reality, they did something even more fundamental. They began calming the entire planet. Water absorbs heat remarkably well. During the day, the oceans collected enormous amounts of warmth. Later, they released that heat much more slowly than bare rock could. Almost without anyone noticing, the oceans became Earth's first great climate regulator, smoothing out extremes and creating a more stable environment than the violent landscape that had come before. In another quiet way, the oceans also became a shelter. Above the surface, harsh ultraviolet radiation from the young sun still poured down upon the planet. But even a relatively shallow layer of water offered protection from much of that invisible energy. Beneath the waves, temperatures fluctuated less dramatically, and delicate chemical reactions could continue without being interrupted quite so easily. The oceans were not merely beautiful, they were patient. They gave chemistry time. As the surface continued cooling, pieces of Earth's rocky crust gradually became thicker and more stable. Small fragments of ancient continents may have begun emerging above the water, only to change again under the planet's restless interior. The surface was still being rebuilt constantly, but the balance was slowly shifting away from complete destruction. Far below the waves, another remarkable environment was taking shape. In places where seawater seeped deep into newly formed cracks in the crust, it encountered rocks that remained incredibly hot. The water absorbed heat and dissolved minerals before rising back toward the ocean floor. There, dark columns of mineral-rich water poured into the surrounding sea. Today, scientists call these places hydrothermal vents, Rather than thinking of them as strange geological structures, it may be easier to picture them as natural chemical workshops operating continuously beneath the ocean. Warm, mineral-rich water flowed outward, cool seawater flowed inward. Between them existed gentle differences in temperature and chemistry, rather like the difference in height that allows water to turn the wheel of an old mill. Those quiet differences provided a steady source of energy, encouraging countless chemical reactions to happen over and over again. Within tiny pores inside the surrounding minerals, microscopic spaces formed naturally. They were almost like countless miniature rooms, where newly formed molecules could remain close together instead of immediately drifting apart into the enormous ocean. Nothing alive existed there, not yet. But these hidden chambers offered something incredibly valuable: time, energy, water, minerals, and endless opportunities for chemistry to explore new possibilities. The young Earth was no longer simply a planet of fire. Without making any sudden announcement, it had become a world where stone, water, and energy were beginning to cooperate. That quiet partnership would eventually allow something even more extraordinary to emerge, as ordinary molecules slowly started behaving in unexpectedly organized ways, taking the very first steps toward the long story we now recognize as life. The arrival of the oceans did not immediately fill the planet with life. For a very long time, the Earth remained silent. No fish swam beneath the waves. No plants reached toward the sunlight. Even the simplest cell had not yet appeared. The oceans were beautiful only in the sense that a blank canvas is beautiful. They held possibility, but not yet the painting. Still, something important had changed. The young planet finally possessed everything needed to begin experimenting. There was water. There was heat rising from Earth's restless interior. There were minerals constantly released by volcanoes and carried through the oceans. There was energy arriving from sunlight, lightning, and the warm rocks beneath the sea. And above all, there was time, an almost unimaginable amount of time. If we often imagine nature as an engineer carefully following a blueprint, the early Earth suggests something quite different. It behaved more like an artist with an endless supply of paint, willing to try countless combinations until, very gradually, something unexpected emerged. Across the oceans and beneath the atmosphere, simple atoms met one another again and again. Carbon joined with hydrogen, nitrogen combined with oxygen. Tiny molecules formed, broke apart, and formed again. Most lasted only briefly before disappearing. But not all of them. Some became slightly more stable than others. Among these growing collections were simple organic molecules, the kinds of compounds that every living cell still depends upon today. Scientists have spent decades trying to understand how such molecules first appeared, and one famous experiment offered an intriguing clue. In the early 1950s, two researchers, Stanley Miller and Harold Urey, created a miniature version of the young Earth inside a laboratory. They filled a sealed glass apparatus with gases thought to resemble Earth's early atmosphere, added water, and repeatedly sent electrical sparks through the mixture to imitate lightning. After several days, something remarkable happened. The water no longer remained clear. New organic compounds had formed naturally, including amino acids, some of the small molecular building blocks used by living organisms today. The experiment did not create life. It was never meant to. Instead, it demonstrated something profoundly encouraging. The ingredients of biology might emerge from ordinary chemistry under the right conditions. Nature, it seemed, did not require magic, only patience. Of course, the real Earth was far more complicated than a laboratory flask. Lightning may have contributed to these early reactions, but it was probably only one part of a much larger story. Ancient meteorites likely added their own contribution. Some carried carbon-rich compounds that had formed long before the Earth itself existed. Tiny chemical ingredients traveled through space for millions of years before finally landing in the young oceans. quietly adding to the growing collection of possibilities. It is rather comforting to imagine that some of the molecules involved in life's earlier story may have begun their journey among distant asteroids long before our planet was fully formed. Even today, scientists continue discussing where these increasingly complex reactions happened most successfully. One possibility lies deep beneath the oceans. Hydrothermal vents continuously released warm, mineral-rich water into the surrounding sea. Their gentle flow provided steady energy over extraordinarily long periods, creating conditions that remained surprisingly stable despite the chaos elsewhere on the planet. Another possibility is much closer to the surface. Some researchers suggest that shallow pools of water, warmed by the sun and repeatedly filled and dried by changing conditions, may have concentrated molecules more effectively. As the water slowly evaporated, the remaining ingredients were brought closer together, making new chemical reactions easier. At first glance, these ideas may seem to compete with one another. In reality, nature rarely limits itself to only one approach. Perhaps different environments each contributed something unique. Perhaps several pathways quietly unfolded at the same time. The Earth was, after all, an entire planet filled with opportunities. Among these possibilities, the environments surrounding hydrothermal vents remain especially fascinating. It helps to imagine them not simply as underwater chimneys, but as countless natural workshops operating day and night without interruption. Warm, mineral-rich water flowed outward. Cool seawater flowed inward. Between the two existed gentle differences in temperature and chemistry, rather like water flowing from a higher stream toward a lower valley. Those invisible differences continuously supplied energy, encouraging reactions that might otherwise have happened only rarely. The surrounding rocks added another important ingredient. Their tiny mineral pores formed countless microscopic chambers, each one no larger than a grain of dust, yet capable of holding molecules together long enough for increasingly complicated chemistry to unfold. Instead of drifting apart across the vast ocean, molecules found themselves sharing the same tiny rooms, meeting again and again, like neighbors living on the same quiet street. Gradually, chemistry became just a little less random, not because anyone directed it, not because nature had a goal, simply because certain reactions made later reactions more likely. Patterns slowly emerged. Some molecules became surprisingly good at helping other reactions occur. Others became better at remaining intact. The planet was beginning to reward stability. One of the most intriguing ideas proposed by scientists is known as the RNA world. Rather than introducing it as a difficult scientific term, it may be easier to think of it as a chapter in Earth's history when one remarkable kind of molecule possibly learned two jobs at once. It could carry information, and it could help useful reactions happen. Long before the familiar genetic material found in every plant, animal, and person today became dominant, molecules like these may have served as both memory and tool. No one knows exactly how this stage unfolded, but if such molecules occasionally made copies of themselves, something extraordinary would follow almost automatically. No copying process is perfect. Small differences would appear. Some copies would last a little longer. Others would disappear more quickly. Those tiny imperfections, repeated over countless generations, became the first whispers of evolution. Not yet biological evolution as we usually imagine it. Rather, the quiet beginning of selection itself. Another remarkable change arrived almost unnoticed. Certain fatty molecules floating in water naturally arranged themselves into delicate spheres. No outside force organized them. No hidden instructions guided them. Just as tiny droplets of oil gather together when mixed with water, these molecules quietly assembled into thin, protective bubbles. Inside each bubble, chemical reactions could remain close together instead of immediately dispersing into the surrounding ocean. It was rather like carrying a small workshop inside a transparent soap bubble. These fragile structures were not truly alive. Scientists often call them protocells, meaning simple predecessors of living cells. Yet they offered something precious, a boundary. For the first time, there was an inside and an outside. The chemistry within these tiny spheres could continue for longer, protected from the endless mixing of the open sea. The Earth had not yet created life, but it had begun creating places where life might eventually become possible. Without making any dramatic announcement, the planet's countless chemical experiments were slowly growing more organized, more persistent, and ever so slightly more capable of remembering what had worked before. In that quiet persistence, the boundary between chemistry and biology was beginning to soften, almost too gently to notice, yet enough to change the future of an entire world. There is no single morning in Earth's history when the first living cell suddenly appeared. No sunrise marked the occasion. No mountain witnessed the event. The transition was almost certainly so gradual that, if someone could have watched it unfold in real time, they might never have noticed the exact moment when chemistry became biology. Instead, countless tiny experiments continued across the young planet. Some lasted only moments. Others endured a little longer. Most disappeared forever. But every now and then, one small improvement remained. A slightly stronger boundary, a more reliable reaction, a better way of using the surrounding energy. Over unimaginable spans of time, these small improvements accumulated until something entirely new emerged. The earliest living cells were astonishingly simple. Compared with the cells inside your body today, they would have seemed almost empty. They contained no intricate internal structures, no specialized compartments, and no remarkable complexity. They were little more than delicate membranes surrounding a small collection of molecules working together just well enough to remain organized. Yet simplicity should never be mistaken for weakness. These tiny pioneers accomplished something no collection of molecules had ever achieved before. They persisted, they grew, and, most importantly, they reproduced. When one of these primitive cells divided, it passed its chemical instructions to two descendants. The copying process was not perfect, and that imperfection became one of life's greatest strengths. Every small difference created another possibility. Some descendants functioned slightly better, others struggled. Without intention, without planning, and without any destination in mind, natural selection had quietly begun shaping the future. Scientists believe that all living organisms on Earth may ultimately trace their ancestry back to a remarkably ancient population of early cells. This ancestor is not thought to have been the very first form of life. Instead, it represents the oldest common branch from which every living organism known today eventually descended. Researchers refer to this ancient ancestor by the name Luca, short for the last universal common ancestor. Although the name sounds highly technical, the idea itself is surprisingly simple. Imagine tracing your family tree backward through generation after generation until distant branches slowly merge together. Eventually, you arrive at a shared ancestor connecting countless descendants. Luca occupies a similar place in the story of life. Every tree, every mushroom, every whale, every eagle, every person reading these words. Somewhere in the unimaginably distant past, all of us share that ancient biological connection. Of course, the world Luca inhabited would have been almost unrecognizable to us. There was still no oxygen filling the atmosphere. To modern humans, such an environment would be impossible to survive. Yet for Earth's earliest life, oxygen was not missing. It simply wasn't needed. Instead of breathing oxygen, these ancient organisms obtained energy through entirely different chemical pathways. They lived among minerals, warm water, and naturally occurring chemical differences that surrounded them beneath the oceans. It is another reminder that life rarely begins by demanding perfect conditions. It begins by making use of whatever conditions already exist. Deep beneath the sea, hydrothermal vents continued supplying warmth and fresh minerals. Warm water rich in hydrogen mixed with cooler seawater carrying dissolved carbon compounds. Wherever these different environments met, energy naturally flowed from one state toward another. Rather like water flowing downhill without anyone pushing it, chemical energy moved wherever differences existed. The earliest cells learned to take advantage of those gentle flows. They did not create the energy, they simply learned how to use it. This marked another quiet revolution. Life was no longer depending on isolated chemical reactions that happened only by chance. Instead, reactions began linking together into repeating cycles. One reaction prepared the next supported another. Eventually, the entire sequence could continue again and again, much like an old water wheel that keeps turning as long as the river continues flowing beside it. These early metabolic cycles gave primitive cells something incredibly valuable: reliability. The environment remained unpredictable. The chemistry inside each cell became just a little more dependable. Another equally important innovation was taking shape. The membrane surrounding each cell gradually became more than a simple boundary. It became a gatekeeper. At first, molecules moved freely across it, but over time, cells that controlled what entered and what remained inside gained an enormous advantage. Imagine trying to keep a warm room comfortable during winter. If every door and window remained open, the warmth would quickly disappear. But if the house could gently regulate what entered and what stayed inside, it would become far easier to maintain a stable environment. Early cells slowly learned a similar lesson. They created a tiny world within themselves. Outside remained unpredictable. Inside became increasingly organized. That distinction between inside and outside remains one of the defining characteristics of every living cell today. The oceans still tested these fragile organisms constantly. Temperatures changed, volcanoes erupted, mineral concentrations shifted. Occasional asteroid impacts still disturbed the surface above. Entire populations must have disappeared countless times, yet extinction and survival became partners in life's long education. Every failure quietly revealed another possibility. Every survivor carried a slightly improved solution into the future. Some ancient communities even began forming layered structures along shallow coastlines. Generation after generation of tiny microorganisms trapped fine sediments while continuing to grow, slowly building rocky formations that accumulated over extraordinary spans of time. Today, these structures are known as stromatolites. Although they may appear to be ordinary rocks, they are among the oldest visible records of life on our planet. Some examples still exist today, offering a quiet connection between the modern world and a biological story that began billions of years ago. Perhaps the most remarkable feature of these earliest organisms was not their appearance, it was their patience. For hundreds of millions of years, life remained microscopic. There were no giant creatures, no forests, no flowers. The greatest achievements of biology unfolded entirely beyond the reach of human eyes. If you had somehow visited Earth during this immense span of time, you might have concluded that almost nothing was happening. Yet beneath that apparent stillness, evolution continued refining countless invisible experiments. Every successful cell became the starting point for another possibility. Every generation explored another tiny variation. The pace was almost impossibly slow, and yet it never truly stopped. Eventually, among those countless microscopic descendants, one lineage stumbled upon an innovation that would transform not only life itself, but the entire planet. Instead of relying solely on chemical energy hidden within rocks and minerals, these tiny organisms began reaching toward a completely different source of power. They learned to harvest sunlight. That quiet discovery would alter the atmosphere, reshape the oceans, and prepare Earth for every complex form of life that would follow. For an extraordinarily long time, the world remained comfortably familiar to its earliest inhabitants. The oceans were filled with microscopic life, quietly dividing, adapting, and evolving beneath the waves. Their surroundings changed constantly, yet the basic rules of survival remained much the same. Energy came from chemical reactions deep within the earth, from minerals carried through warm water, and from the endless exchange between the planet's rocky interior and its oceans. Life had become remarkably good at living in that ancient world, but evolution rarely stops searching for new possibilities. Among countless generations of tiny microorganisms, one group gradually stumbled upon an entirely different source of energy. It was shining overhead every single day: sunlight. To us, sunlight feels so ordinary that it is easy to forget how extraordinary it truly is. Every morning, it slips quietly across the landscape, warming the ground, illuminating forests, and reflecting from rivers and oceans without asking for anything in return. Yet hidden inside every beam of light is an immense amount of energy. Some ancient microorganisms slowly learned how to capture a small fraction of that energy and use it to build the molecules they needed for life. Today, scientists know these remarkable pioneers as cyanobacteria. Despite their impressive name, they were astonishingly simple organisms. There were no leaves, no roots, no flowers reaching toward the sky, only tiny cells floating through shallow seas, quietly performing a chemical process that would reshape an entire planet. At first, nothing about this new strategy seemed especially dramatic. The organisms themselves remained microscopic. Their colonies spread slowly. The oceans continued rolling quietly against ancient shores. If you had visited Earth during this period, you almost certainly would not have noticed anything unusual. Yet every day, these tiny organisms were releasing something that had rarely existed in significant amounts before: oxygen. Ironically, oxygen was not their goal. It was simply a leftover product. Much like sawdust accumulating beneath a carpenter's workbench, or steam rising from a kettle while water boils, oxygen was merely the byproduct of another process. The cyanobacteria had no intention of transforming the planet. They were simply surviving. Nature often changes the world in exactly this quiet way. No grand design, no deliberate plan, only countless small actions repeated over immense spans of time until the consequences become impossible to ignore. At first, the newly released oxygen seemed to vanish almost immediately. The ancient oceans contained enormous quantities of dissolved iron, carried there over millions of years from Earth's young crust and active volcanoes. Whenever oxygen entered the water, it eagerly combined with that dissolved iron. The result was rust, not the familiar reddish flakes that slowly appear on an old bicycle left in the rain, but vast quantities of newly formed iron minerals settling gently onto the ocean floor. Layer after layer accumulated over millions of years. Dark minerals, dark again, then reddish once more. Like pages quietly added to an unimaginably old diary, these layers recorded one of the greatest environmental transformations in Earth's history. Today, geologists call them banded iron formations. Even now, they remain preserved within ancient rocks, allowing scientists to read events that unfolded billions of years before the first animals ever existed. For an incredibly long time, the oceans continued absorbing nearly all of the oxygen being produced. It was almost as though the planet possessed an enormous sponge. Every new supply disappeared into it. Eventually, however, that sponge became saturated. The dissolved iron had largely been transformed. The oceans could no longer consume oxygen as quickly as before. For the first time, increasing amounts of oxygen began escaping into the atmosphere, slowly, quietly, almost imperceptibly. Yet the consequences would be profound. To modern life, oxygen is associated with vitality. We breathe it every moment without giving it much thought. But to Earth's earliest organisms, oxygen was anything but friendly. In fact, it was dangerous. Many ancient microbes had evolved in a world completely without it. Their delicate chemistry had never learned to cope with this highly reactive gas. As oxygen concentrations gradually increased, countless species found themselves living in an environment that had become increasingly hostile. One of Earth's greatest biological crises had begun. Scientists sometimes refer to this transformation as the Great Oxidation Event. The name sounds dramatic, yet the process itself unfolded over hundreds of millions of years. There was no single catastrophic day. Instead, countless microscopic tragedies accumulated gradually. Entire communities disappeared. Others retreated into environments where oxygen remained scarce, such as deep sediments beneath the oceans or underground habitats. Remarkably, some of their descendants still exist today, quietly preserving lifestyles that originated billions of years ago. Yet evolution once again demonstrated its remarkable resilience. While some organisms struggled, others slowly adapted. A few discovered that oxygen, despite its dangers, could become an astonishingly powerful ally. Used carefully, it allowed cells to extract far more energy from food than earlier chemical pathways had ever managed. Imagine replacing the gentle flame of a candle with the steady warmth of a well-built fireplace. Both produce heat, but one provides far more energy while remaining carefully controlled. Cells capable of managing oxygen suddenly possessed a much larger energy budget for growth, repair, and future innovation. The atmosphere itself continued changing. As oxygen accumulated high above the planet, sunlight triggered new reactions that gradually formed another invisible layer. This was ozone. Unlike oxygen near the ground, ozone gathered high in the atmosphere, where it quietly absorbed much of the sun's harmful ultraviolet radiation. For billions of years, Earth's surface had been exposed to intense radiation that could easily damage delicate molecules. Now, the planet was slowly constructing its own protective shield. Without intending to do so, microscopic organisms living in shallow oceans had transformed the sky itself. It is one of the most extraordinary partnerships in natural history. The Earth shaped life. Then life began reshaping the Earth. The oceans changed. The atmosphere changed. The chemistry of rocks changed. Even the color of the sky may have slowly become more familiar to modern eyes. The planet that had once been governed almost entirely by volcanoes, impacts, and geology was gradually becoming a world where biology had become an equally powerful force. And as cells learned to harvest more energy than ever before, evolution quietly gained new possibilities. With greater energy came greater complexity. With greater complexity came opportunities that earlier forms of life could never have imagined. Somewhere within that expanding world of microscopic organisms, an unexpected partnership was about to emerge. One so successful that nearly every complex living thing on Earth, including ourselves, still carries its legacy inside every single cell. By now, the Earth had become a very different place from the fiery world where our journey began. The oceans still covered much of the planet. Volcanoes continued shaping the landscape, and continents drifted slowly across the surface. Yet beneath the waves and within shallow coastal waters, life had been quietly rewriting the rules of survival for billions of years. The atmosphere contained more oxygen than ever before. Some organisms had learned to tolerate it. Others had learned to depend upon it. And with that new source of energy came opportunities that had never existed before. For hundreds of millions of years, however, life remained almost entirely microscopic. The oceans were filled with countless single cells, each carrying out its own quiet existence. They competed, they divided, they evolved. Most lived alone. If you could have looked through a microscope at that ancient world, you might have imagined millions of tiny islands floating independently through an endless sea. Then, somewhere among those countless invisible lives, something astonishing happened. It was not a conquest. It was not a battle. It was the beginning of a partnership. One small cell engulfed another. Normally, this would have been the end of the story. One organism would simply digest the other, using it as food. But on this extraordinary occasion, digestion never happened. The smaller cell survived. Instead of becoming a meal, it continued living safely inside its much larger host. At first, this arrangement may have been nothing more than an accident. Yet, accidents sometimes become opportunities. The smaller cell had become remarkably efficient at using oxygen to release energy from food. The larger cell, meanwhile, provided shelter, nutrients, and protection from an unpredictable environment. Each possessed something the other lacked. Neither needed to defeat the other. Together, they became stronger than either could have been alone. Imagine two travelers caught in a long winter journey. One knows how to build a warm fire but has no shelter. The other has built a sturdy cabin but struggles to gather enough fuel. Separately, each survives only with difficulty. Together, their chances improve dramatically. Nature often discovers cooperation long before intelligence ever appears. Over countless generations, the partnership became increasingly permanent. The smaller cell gradually gave up much of its independence. Many of its original genes were transferred into the larger cell. Other abilities simply became unnecessary because its host now provided what it needed. Eventually, the two organisms could no longer live apart. They had become one life. Today, scientists describe this remarkable event with the term endosymbiosis. The word may sound unfamiliar, but the idea behind it is beautifully simple. It means living together on the inside. That ancient guest eventually became what we now call the mitochondrion. Nearly every cell in your body contains hundreds, sometimes thousands of these tiny structures. They are often described as the cell's power stations because they convert food and oxygen into the usable energy that keeps life running. Even now, billions of years later, they still carry subtle traces of their ancient independence. Remarkably, mitochondria possess their own small collection of genetic material, separate from the much larger set stored inside the cell's nucleus. It is almost like finding an old family photograph tucked inside a modern home, quietly reminding everyone of where the family once began. This discovery became one of the strongest pieces of evidence supporting the idea that mitochondria were once free-living organisms. Sometimes, the deepest chapters of history remain hidden in the smallest details. With this new partnership came something evolution had rarely enjoyed before: an abundance of energy. Earlier cells had survived on relatively modest supplies. Now, much larger amounts of energy became available for building increasingly sophisticated structures. It was rather like the difference between operating a small workshop by candlelight and suddenly having reliable electricity flowing into every room. The work itself became more ambitious because far more was now possible. Cells gradually began developing specialized compartments inside themselves. Instead of carrying out every task in one crowded space, different jobs could now happen in different places. Some compartments stored information, others manufactured proteins. Still others packaged and transported materials from one part of the cell to another. A busy city offers a useful comparison. Rather than expecting every building to perform every possible function, cities naturally develop neighborhoods. Markets appear in one area, homes in another. Libraries, hospitals, and workshops each occupy places where they can perform their roles more efficiently. The earliest complex cells slowly developed a similar kind of internal organization. Scientists call these cells eukaryotic cells. Rather than thinking first about the name, it is easier to think about what made them different. They were no longer simple open rooms. They had become carefully organized homes, with different spaces dedicated to different tasks. This organization allowed cells to grow larger without becoming chaotic. More importantly, it opened entirely new possibilities for evolution. Larger cells could carry more genetic information. They could produce a wider variety of proteins. They could respond to changing environments with greater flexibility. Complexity was no longer an obstacle. It had become an advantage. Another quiet innovation soon followed. Instead of simply dividing to produce identical descendants, some cells began exchanging genetic material with one another. This was the beginning of sexual reproduction. Although it sounds like an entirely different story from the one we have been following, it was actually another elegant solution to an ancient problem. Copying the same instructions endlessly limits the number of new possibilities. Sharing genetic information creates new combinations. Imagine 2 decks of cards. If each deck is shuffled only by itself, the patterns remain somewhat familiar. But if the cards are combined before being dealt again, entirely new arrangements become possible. Life had discovered another way to explore. Variation increased. Adaptation accelerated. Evolution acquired an even richer collection of possibilities to test against the changing world. As these increasingly sophisticated cells multiplied across the oceans, something subtle began happening once again. Some no longer remained entirely independent. After billions of years spent perfecting individual survival, certain cells began remaining together after dividing. At first, they formed only small clusters, then larger groups. Eventually, some cells started performing different jobs from their neighbors. One specialized in gathering nutrients. Another became better at protection. A third focused on reproduction. It was cooperation unfolding on an entirely new scale. What had once happened between 2 individual cells was now beginning to happen among entire communities of cells. Without anyone planning it, the foundations of multicellular life were quietly taking shape. The Earth had traveled an astonishing distance from its molten beginning. Atoms had become molecules. Molecules had become cells. Cells had become partners. And partners were slowly becoming living communities. Soon, those communities would face one of the greatest environmental challenges in the history of the planet. A frozen world that, for a time, may have seemed almost beyond recovery. Yet even that immense trial would become another unexpected turning point in the long and patient story of life. By the time complex cells had become firmly established, the Earth had already lived through billions of years of transformation. Its continents continued drifting almost too slowly to imagine. Mountain ranges quietly rose and gradually wore away. The oceans carried minerals from land to sea, then returned them again through the slow movement of the planet's crust. Nothing remained exactly the same for very long. Even so, the world had become far gentler than the fiery planet of its youth. Life continued spreading into new environments. Microscopic communities flourished in shallow seas. Early multicellular organisms were beginning to appear. The future seemed increasingly promising. Then, once again, the planet surprised everyone. Not with fire, but with ice. Scientists believe that several times during Earth's distant past, the climate cooled so dramatically that enormous ice sheets expanded from the poles toward the equator. One of these episodes may have been so severe that nearly the entire planet became wrapped in ice. This remarkable idea is known as the snowball Earth hypothesis. The name paints a vivid picture, but the reality was probably even more astonishing. Imagine standing on a frozen lake during the quietest morning of winter. Everything appears still. The landscape reflects soft light in every direction. Sound seems to travel differently across the cold air. Now imagine that peaceful frozen surface extending not for a few kilometers, nor across a single country, but across nearly an entire planet. The oceans themselves may have worn an enormous shell of ice. The continents disappeared beneath brilliant white landscapes. Even regions near the equator, which today receive intense tropical sunlight, may have remained locked beneath frozen expanses. At first, such a world seems completely incompatible with life. How could anything survive? The answer may lie in the remarkable resilience that life had already developed over billions of years. The ice covering the oceans was likely thick, but not necessarily solid all the way to the seabed. Far below the frozen surface, liquid water could still exist. The Earth's interior never stopped producing heat. Hydrothermal vents continued releasing warm, mineral-rich water from deep within the crust. Tiny ecosystems that had depended on these underwater environments for hundreds of millions of years may have continued living almost as if nothing had changed above them. In other places, sunlight may still have reached patches of relatively thin ice, or areas where shifting conditions created temporary openings. Life did not need an entire planet of favorable conditions. It only needed small refuges. A quiet valley, a warm spring, a protected coastline. Nature has often demonstrated that survival begins not with abundance, but with persistence. Of course, the frozen Earth created enormous challenges. Weathering slowed dramatically as rocks became buried beneath ice. Many shallow marine habitats disappeared. Populations that had once been connected became isolated from one another. Countless organisms almost certainly vanished forever. Yet isolation sometimes encourages innovation. Imagine several small villages separated by heavy snowfall throughout an unusually long winter. Each community must solve similar problems, but not necessarily in the same way. Over time, each village develops its own customs, techniques, and traditions. When the roads finally reopen, those communities are no longer exactly alike. Something similar may have happened to life during these great ice ages. Separated populations continued evolving independently. Small differences accumulated generation after generation. Then, eventually, the climate began changing once again. The reason appears to involve one of Earth's oldest geological processes. Although the surface remained frozen, volcanoes never stopped erupting. Deep beneath the ice, Earth's interior continued releasing carbon dioxide into the atmosphere. Normally, rainfall slowly removes much of that carbon dioxide by reacting with rocks and carrying dissolved minerals into the oceans. But on a frozen planet, rainfall became extremely limited. Rock weathering nearly stopped. As a result, carbon dioxide gradually accumulated in the atmosphere over millions of years. Rather like adding another blanket during a cold night, the atmosphere slowly trapped more and more heat. Not immediately, not dramatically, but patiently. Eventually, enough warmth accumulated to overcome the planet's icy grip. The thaw may have happened surprisingly quickly by geological standards. Ice retreated. Dark oceans once again absorbed sunlight. The warming accelerated. Water flowed across freshly exposed continents that had remained frozen for millions of years. Those newly uncovered rocks contained enormous quantities of minerals. Rain and rivers carried them into the oceans, where they became valuable nutrients for countless microscopic organisms. It was almost as though the planet had spent millions of years quietly filling a storehouse before suddenly opening the doors. The oceans responded, life responded, productivity increased, food became more abundant. New ecological opportunities appeared almost everywhere. Not long afterward, Earth witnessed another remarkable chapter in its history. Large, soft-bodied organisms began appearing in the oceans. Today, fossils from this period are known as the Ediacaran biota. Some resembled leaves resting gently upon the seafloor. Others looked like delicate feathers or quilted cushions. Many possessed body shapes unlike anything alive today. They remind us that evolution often explores possibilities that later disappear completely. These organisms were not yet the familiar animals we know. They had no hard shells, no powerful jaws, no rapid movement. Yet they represented something profoundly important. Life was beginning to occupy space in entirely new ways. Bodies became larger. Communities became more complex. Relationships between organisms became increasingly intricate. The stage was quietly being prepared once again. Then, over a comparatively short span of geological time, evolution seemed to accelerate. Scientists refer to this extraordinary interval as the Cambrian explosion. The word explosion can sound sudden, but even this transformation unfolded over tens of millions of years. Still, compared with the slow pace of earlier evolution, the change was astonishing. Animals developed hard shells that protected their soft bodies. Some evolved flexible limbs for crawling across the seafloor. Others became active swimmers. Eyes capable of detecting light and movement appeared in multiple evolutionary lineages, opening an entirely new way of experiencing the world. For the first time, predators and prey began influencing one another in an ongoing evolutionary conversation. Better vision encouraged better camouflage. Stronger jaws encouraged stronger defenses. Every new adaptation inspired another. The oceans, once inhabited almost entirely by microscopic life, had become dynamic ecosystems filled with movement, competition, and astonishing diversity. The Earth had traveled an extraordinary path. A frozen world had not ended life's story. Instead, it had quietly rewritten its next chapter, preparing a richer and more complex future than anyone could have imagined. Soon, those countless branches of evolution would continue spreading across the oceans, onto the land, and eventually into the skies, each carrying within them the memory of a planet that had learned, again and again, how to transform challenge into possibility. When we look at the Earth today, it is easy to believe that it has always been this way. Blue oceans wrap around the continents, clouds drift peacefully across the sky, forests rise from fertile soil, birds cross the morning air, while waves roll gently onto familiar shores. Everything feels settled, almost inevitable. Yet nothing about this world was inevitable. Every mountain, every ocean, every forest, and every living creature exists because countless events unfolded in just the right sequence across more than 4.5 billion years. If even one chapter had been dramatically different, the story we know today might never have been written. The molten oceans that once covered the planet slowly cooled into solid crust. Volcanoes filled the atmosphere with gases that later helped create clouds and rain. Water gathered into oceans that protected fragile chemistry. Simple molecules slowly organized themselves into structures capable of making imperfect copies. Those tiny imperfections became evolution. Evolution produced cells. Cells formed partnerships. Partnerships became increasingly complex communities. Microscopic organisms transformed the atmosphere. The atmosphere protected future life. Again and again, the Earth did not move toward a predetermined destination. Instead, every stage created new possibilities that had never existed before. Looking back across this immense history, one idea quietly appears again and again. Life did not simply adapt to the planet. The planet and life transformed one another. In the beginning, geology shaped biology. Volcanoes, oceans, continents, and the atmosphere determined what kinds of organisms could survive. Later, biology began shaping geology in return. Tiny microorganisms released oxygen that altered the chemistry of the oceans. They changed the composition of the atmosphere. They helped create the protective ozone layer high above the Earth. Much later, forests would influence rainfall, plants would help shape soils, coral reefs would build entire underwater landscapes. Even today, billions of living organisms continue influencing the climate, the oceans, and the cycling of nutrients across the globe. Earth is not simply a planet that contains life. It is a planet that has grown together with life. Each has spent billions of years quietly changing the other. Perhaps one of the most astonishing parts of this story is that its earliest chapters have never truly disappeared. Every cell inside your body still carries reminders of those ancient beginnings. Your cells continue surrounding themselves with carefully regulated membranes, just as the earliest cells learn to separate their inner chemistry from the outside world. Deep inside almost every one of your cells, mitochondria continue producing usable energy, preserving the legacy of that remarkable partnership formed billions of years ago. Even your genetic material still follows principles that emerged during Earth's earliest biological experiments, copying itself with extraordinary accuracy while allowing just enough variation for evolution to continue across generations. Your body is not separate from Earth's history. It is one of its newest chapters. In a quiet sense, every heartbeat echoes decisions that evolution has been refining since long before animals, plants, or even oxygen-rich skies existed. Sometimes we imagine ancient history as something completely disconnected from everyday life, something locked inside museums, fossils, or distant layers of rock. Yet every ordinary moment quietly tells the same story. When you drink a glass of water, some of those water molecules may have circulated through Earth's oceans for millions of years before eventually reaching you. When you breathe, the oxygen entering your lungs exists because countless generations of microscopic organisms slowly transformed the atmosphere long before dinosaurs walked the Earth. When you eat a piece of fruit, its energy ultimately comes from sunlight captured by photosynthesis, a process whose earliest ancestors first appeared billions of years ago in tiny cells floating through ancient seas. The oldest chapters of Earth's history are not gone. They continue unfolding inside every ordinary day. This perspective also changes the way scientists search for life beyond our own planet. For many years, people naturally asked a simple question: does another world have life? Today, researchers often begin with an earlier question: does another world possess the conditions that allow chemistry enough time to become biology? Liquid water remains one of the most important clues. Not because water itself is alive, but because it provides an extraordinary environment where molecules can meet, separate, combine, and try again over immense stretches of time. Scientists also search for planets with stable climates, protective atmospheres, sources of energy, and chemical ingredients similar to those that once existed on the young Earth. The search has become less about finding creatures that resemble us and more about discovering worlds capable of beginning long journeys of their own. Thousands of planets have already been discovered orbiting distant stars. Some are enormous worlds larger than Jupiter. Others are rocky planets that may resemble the early Earth. Most will probably never become living worlds. Some perhaps already have. We simply do not know yet. That uncertainty is strangely comforting. It reminds us that our own story is part of a much larger universe still waiting to be understood. As telescopes grow more powerful and our understanding deepens, we continue searching not merely for another Earth, but for another place where fire, water, chemistry, time, and chance may have slowly woven themselves into something capable of asking questions about its own existence. Perhaps that is one of the quiet miracles hidden within this long history. The universe produced stars. Stars forged the elements. Those elements gathered into planets. One of those planets spent billions of years transforming itself through geology, chemistry, and evolution until, eventually, living beings emerged who could guide. In that sense, the Earth has done something extraordinary. After billions of years of change, it has become a world capable of remembering its own past through the minds of the creatures it helped create. And perhaps that is the gentlest thought to carry with you tonight. The atoms that make up your body were once part of ancient stars. The water flowing through your cells has been traveling across this planet for ages beyond imagination. The energy keeping every heartbeat alive began its journey in sunlight that first touched leaves, whose distant ancestors learned their craft in oceans older than memory. You are not standing outside this story. You have always been part of it. As the day quietly fades and your thoughts begin to settle, perhaps it is comforting to remember that the Earth has never stopped changing. Neither has life. For billions of years, both have moved forward together with remarkable patience, one gentle transformation leading almost invisibly to the next. And tonight, as you rest beneath a calm sky that was once filled with fire, you become, for a little while, another peaceful moment in that endless journey. Good night.